This chapter is called How Derivatives Affect the Shape of a Graph. So we're going to start with information we can gather about the function f of x from its derivative f prime of x. So we know that f prime of x, the derivative, represents the slope of the curve at each point, which tells us the direction in which the curve proceeds at that point. So starting here with something that we call the increasing or decreasing test, if we take the derivative and f prime of x is positive on an interval, that means the function is increasing on the interval. Also, if we take the derivative and the derivative is negative on an interval, that means the function is decreasing on the interval. So positive derivative, function is increasing. Negative derivative, function is decreasing. So hopefully that makes sense if you think about the derivative is the slope. If we have a positive slope, then it would look like that, which means positive derivative, so it's increasing. If we have a negative slope, it would look something like that, which means negative derivative. The function is decreasing. So now moving on to the first derivative test, but before we take a look at this test, we need to remember something about critical numbers. So recall that if we have a local max or a local minimum at an x value of c, then c must be a critical number. And remember that a critical number, c, would be f prime of c equals 0, or the derivative f prime of c does not exist. So what we're going to do is we're going to have to find some critical numbers here. And since every critical number does not necessarily have to be a max or a min, we're going to have to test them to see if they are a max or a min. And this is where the first derivative test comes in. The first derivative test is going to help us determine relative max and relative min. So first, what we're going to have to do is we're going to have to find the critical numbers. So suppose that we found the critical numbers, which once again is taking the derivative, setting it equal to 0 and solving, and also seeing where the derivative does not exist. Once we have those values, if f prime changes from positive to negative, meaning it's increasing and then decreasing, that means there has to be a local or relative max at that point c, at that critical number. Also, if f prime changes from negative to positive, meaning the function changes from decreasing to increasing, there would be a relative minimum at c. There could also be the case that it changes from, or it goes from increasing and then it remains increasing at that critical value c. In that case, there would be no relative max or min. Similarly, it can be decreasing and then we get the critical point and then it continues decreasing and there would be no relative max or relative min. So here are the graphs right here, which I essentially just drew right above. The first one, A over here on the left, we can have a local max if it goes from increasing to decreasing. And then the second one, we have a local min if it goes from decreasing to increasing. Third one, we have neither a max nor min because it goes from increasing, flattens out, and then stays increasing. Last one, no max or min, decreases, flattens out, and then continues decreasing. Okay, so that is the first derivative test. It tells us whether or not we have a relative max or relative min. So let's do an example. Let's find where the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. We're going to find where it's increasing and decreasing and find any relative max or min using the first derivative test. Okay, so first derivative test, we need to first find the critical numbers. So that's two things. We need to take the derivative, set it equal to 0 and solve, and then we need to find when the derivative does not exist, and that won't always give us values, but we have to remember to try to do that. Okay, so first let's take the derivative. So f prime of x, take the derivative of this function. We get 12x cubed minus 12x squared minus 24x. So there's our derivative. Now we're going to set this derivative equal to 0 and solve. So we set f prime equal to 0. That's going to be 12x cubed minus 12x squared minus 24x. So remember, we're doing this to find the critical numbers because if the derivative equals 0, that means the slope equals 0, which would be a horizontal tangent line. And solving this, we can find a GCF of 12x, factor that out front. We'd be left with x squared minus x minus 2 equals 0. We can factor that quadratic as x minus 2 times x plus 1. And then we set each one of those factors equal to 0 separately. And solve, we should end up getting negative 1, 0, and 2. So these are critical numbers. And to try to find the other critical numbers, we try to see where this derivative would not exist. This derivative exists for all real numbers from negative infinity to infinity because it's a polynomial. So we actually do not have to worry about that portion for this one. Okay, so what we do next here with the critical numbers, we don't know if these numbers represent relative max or relative min. We don't know yet. We have to check. So the way that we check is we actually do this number line. So we create a number line, and this, if you want to call it something, you can call it the increasing or decreasing test from the previous page. So increasing, decreasing test, we take the critical numbers that we just found, negative 1, 0, 2, just, you don't have to have it perfect, I just evenly space them out. So what we're going to do here is we just created 4 different intervals, right? We created an interval here, here, and here. What we're going to do is we're going to pick test values in these intervals. So we're going to pick a number here, pick a number here, pick a number here, pick a number here, and we're going to plug those values into the derivative and see if they give us a negative or a positive, and that will tell us if our function is increasing or decreasing. So let's go ahead and pick values. So picking something to the left of negative 1, negative 2 works. You could have picked negative 3, you could have picked negative 4. Picking a number between negative 1 and 0, I would pick negative 1/2. Picking a number between 0 and 2, I'll pick 1. Picking a number greater than 2, we'll pick 3. So once again, you could have picked any numbers as long as they were in those correct intervals. Try to pick the easiest ones to plug in though. Okay, so what we're going to do now is we're going to plug them into the function. So here's the derivative. We're going to plug all of those test points into the function and see if they give us a positive or negative value. So we need to evaluate f prime of negative 2, f prime of negative 1/2, f prime of 1, and f prime of 3. Okay, so let's start with negative 2. Where's our derivative? Our derivative is right here. So we plug in a negative 2. That's going to be 12 times negative 2 cubed minus 12 times negative 2 squared minus 24 times negative 2. So we don't care what the actual value is. We only care if it's negative or positive. So if you evaluate this, you would see that you get a negative number. So what I'm going to do now is with that information, I'm going to go back up to this number line and I'm going to say f prime is going to be this lower part and then f is going to be the top part. So we just found that for negative 2, we found that the derivative was negative. So what that means is that the function is decreasing. So you could write decreasing if you want. I like to just draw a line that is decreasing. Okay, so the next one, if we evaluate f prime of negative 1/2, I'll leave that to you guys to plug in. But if you evaluate that, you get a positive value. So f prime of negative 1/2 is positive. That means f is increasing. If we take a look at f prime of 1 and we plug that in, we would see that this is negative. So negative value for f prime of positive 1. F is decreasing. Lastly, for 3, plug that in, we would get a positive value. So that's positive, so the function is increasing. Okay, so before we take a look at the graph that's right there, this test tells us, this little number line right here tells us everything we need to know that the question's asking. It tells us the intervals for increasing and decreasing, and it also tells us the relative max and relative min. So let's take a look at the intervals for increasing and decreasing first. So we know a function is well, we can see it right here. So let's just take a look. We have increasing for these intervals right here. That's going to be increasing on the intervals -1 to 0, union 2 to infinity. So I'm using interval notation. So it was just -1 to 0 and then 2 to infinity. So that's increasing. Decreasing, we have these intervals right here, which is going to be -infinity to -1, union 0 to 2. Okay, so that's our intervals for increasing and decreasing. Now we're going to take a look and find the relative max and the relative min. So relative max and relative min, we know that a function has a relative max if it changes from increasing to decreasing. So it changes from increasing to decreasing at this critical number of 0. So that means the relative max is going to be at the point 0. And if we want to find the y-coordinate, we would have to evaluate f of 0. So go back up to the original function, plug in 0, you'd end up getting 5. Okay, next, relative min. We know a function has a relative min if it changes from decreasing to increasing. That happens at these two critical numbers. So remember that the relative max and relative min are going to happen at our critical numbers, maybe. So we have a relative min at -1, and if we want the y value, go ahead and plug it in the original function, and we'd actually get 0. So -1, 0. And then we have another relative min at the critical number 2. Go ahead, plug that in, and we would get -27. Okay, so this is the first derivative test, and inside this first derivative test, we also did the increasing and decreasing test. And you can see we have our graph right here for the function. We can see that it's decreasing, increasing, decreasing, increasing, which our number line told us. We can see that we have a relative min at -1, 0, and 2, -7, and a relative max at 0, 5. Okay, so let's do another one. We want to find the local max and minimum values of the function g of x equals x plus 2 sine of x on the interval 0 to 2 pi. So first we're obviously doing the first derivative test here. So first we need to find the critical numbers, which we know we're finding the c values where f prime equals 0 and f prime does not exist. I'll just write that as an or. Okay, so taking the derivative, we want g prime of x, the derivative of x is 1. The derivative of sine is cosine. So the derivative is 1 plus 2 cosine x. And now we take this and we set g prime equal to 0, and then we try to solve it. So we have 1 plus 2 cosine x equals 0. And now we have to remember how to solve trig equations. We need to isolate cosine, subtract 1 on both sides. We get 2 cosine of x equals -1. Divide both sides by 2. Cosine of x equals -1/2. And this is where your trig information needs to be recalled here. We need to think, when does cosine of x equal -1/2 on the interval 0 to 2 pi? So there's always a couple options you can do these types of questions with trig. If you have the unit circle memorized, you can fill out the unit circle and you'll find these values. Another way to do it is going to be draw out the graph of cosine from 0 to 2 pi, which would look something like this. We know that 2 pi is here, halfway is pi, here's 3 pi over 2, and here is pi over 2. So we're trying to say for what values of x will give us out a y value of negative 1/2. Here's negative 1/2. So we go over to the function. So that means we're looking for this value right here, as well as this value right here. So the way that you can think about this is you can go back to the first quadrant. So if you remember, maybe in a trig class, you would get the little table with degrees and radians from 0 to pi over 2 or 0 to 90 degrees. You'd have every trig function evaluated at those angles. Those angles are all in quadrant 1. Quadrant 1 in this case is 0 to pi over 2, so it's this whole sliver right here. So what we can actually do is we can use that first quadrant and then use symmetry of cosine, the periodicity of cosine, to help us figure out cosine of x equals negative 1/2. So what we have to do is we can say, when does cosine of x equal positive 1/2 in quadrant 1? And this will actually help us if you remember this one, because this one's one that hopefully we do know for quadrant 1. This gives us a value of x equals pi over 3. Cosine of pi over 3 equals 1/2. So what we can do from there is we notice that this first answer is in quadrant 2. The second one is in quadrant 3. If we know that our answer would be pi over 3 in quadrant 1 using positive 1/2, then in quadrant 2, we base it around this pi right here. It would be pi minus pi over 3, which is 2 pi over 3. And then this value would be pi plus pi over 3, which is 4 pi over 3. Okay, so definitely pretty tricky if you're not good with trigonometry. So that's our x values. X is going to equal 2 pi over 3 and 4 pi over 3. So these are our critical numbers. And we should also notice that g prime exists everywhere from negative infinity to infinity. So there's g prime. So we don't have to worry about finding values that make g prime not exist. So those are our critical numbers. Now we can move forward using the increasing decreasing test. So we're going to create our number line, and we have our critical numbers of 2 pi over 3 and 4 pi over 3. This bottom portion, well, first we're going to choose numbers on these intervals right here, here, and here. And this bottom portion is going to represent g prime, and the top portion is going to represent g. So we need to pick our test points here, here, and here, such that they are still in the interval 0 to 2 pi. So we have to be careful. We have to make sure that we're still going to be in the interval 0 to 2 pi. Well, something that's pretty easy if you already drew this out right here, we can use this value of pi over 2, this value of 3 pi over 2, and then right between them, that value of pi. So let's go ahead and use those as our test points here. We have pi over 2, pi, and 3 pi over 2. So once again, these aren't the only ones that we could have used, but in my opinion, these ones are probably the easiest ones to use. And then we have to test these points I'll just go ahead and write them out here. So we need to evaluate g prime of pi over 2, see if it's positive or negative. Same thing with g prime of pi. Same thing with g prime of 3 pi over 2. So if you go ahead and you've plugged these in the derivative and evaluate them, once again, we just care if they're positive or they are negative, we would see that we would get positive, negative, positive. So go ahead and test that on your own. So that would be positive, which means g is increasing, negative, g is decreasing, and positive, g is increasing. So from this information, we now know our relative max and relative min, and we could find the intervals for increasing and decreasing, obviously, but this question just asks for relative max and relative min. We know that we have a relative max at this critical value because it changes from increasing to decreasing, so a relative max at 2 pi over 3. And let's go ahead and find the y value. We could find the y value by plugging that directly into the original function. If we did that, we'd get kind of this nasty value, 2 pi over 3 plus radical 3, which we can leave just like that. And for the relative min, when it changes from decreasing to increasing, that's at this critical number, which is 4 pi over 3. Go ahead and plug that into the original function, and we would get 4 pi over 3 plus radical 3. Or sorry, that should be minus radical 3. So 4 pi over 3 minus radical 3 for that y value. So there we go. That's one relative max and one relative min. And we can see on the graph that we have here, here's the relative max at 2 pi over 3. Here's the relative min at 4 pi over 3. Okay, so that was using the first derivative test once again. Now we're going to see how the second derivative, f double prime of x, affects our function f of x. So the first thing that we're going to do with the second derivative is the second derivative test. The second derivative test is going to be an alternative to the first derivative test. It's going to help us identify local max and min values. Okay, so the second derivative tells us that if f double prime is continuous near c, and if f prime of c, so the first derivative of c equals 0, and f double prime of c is positive, then that means we have a local min at that c value. And then if we also have f prime of c equals 0, but f double prime of c is negative, then that means it's a local max at that value. So what we're going to do is we're going to take the derivative and set it equal to 0 and solve, just like we did before. We're going to get a value, but then we're going to take the derivative of the function again to get the second derivative. We're going to plug our c value into the second derivative and see if it's positive or negative. So the reason why if we have f double prime of c is positive, we're going to see in a second, we're going to work with concavity, as you can see this word concave up right here. If it's f double prime is positive, it might look something like this, and we'll see why in a second. So if it looks something like that, then you can see why we would have a minimum, a local minimum value. If f double prime of c is negative, then it might look something like this. Once again, we'll see why that is in a minute. And then hopefully you can see why that would result in a relative maximum value. Okay, so let's go ahead and find the relative max and min of this function using the second derivative test. So first we have to take the derivative and set it equal to 0. This is actually the function that we did a couple pages ago. So we take the derivative, set it equal to 0. The derivative is 12x cubed minus 12x squared minus 24x. And we set it equal to 0. And I'll go a little bit fast here because we already did this one. We have to factor this, and we get this, and then we factor that quadratic to x minus 2 times x plus 1. And that gave us the x values, the critical values of -1, 0, 2. Now what we have to do, so before what we did the first derivative test. Now we're going to do the second derivative test, which means we take the second derivative. So we take the second derivative based on the first derivative. We get 36x squared minus 24x minus 24. And all we have to do with the second derivative now is we have to evaluate the following. We need to evaluate f double prime of -1, 0, and 2. So we need to evaluate f double prime of -1. Move this over. So that's going to be 36 times -1 squared minus 24 times -1 minus 24. And we don't actually care the exact value. We would get a positive 36 out. We just care if this is positive or negative. So I'll just put equals 36, and 36 is positive. So what that means is since f prime of -1 equals 0, and f double prime of -1 is positive, that means we have a relative minimum value at x equals -1. Okay, let me just move this around so I have more room. Okay, so we would do the same thing for the next two. We would do the same thing for f double prime of 0. So if we plugged in a 0, we would get -24, which is obviously negative. So that's going to mean that we have a relative max at x equals 0. And lastly, if we do it for the last critical number of 2, if we plug that in, we would see that it ends up being positive. And if it's f double prime of the critical number is positive, that means a relative min at that value. Okay, so there's our 3 relative extreme points. If you wanted to, you could find the y values like we did before, go back and plug them in the original function. Okay, let's do one more like this. We have g of x equals x squared minus 3x plus 1. So first we take, we're doing the second derivative test, we're going to find the first derivative. G prime of x equals x squared minus, g prime of x taking the derivative equals 2x minus 3. Now we're going to set this equal to 0 and solve to find the critical values. So we get 2x minus 3 equals 0. Add 3 to both sides and then divide both sides by 2. We get x equals 3 over 2. So now let's go ahead and take the second derivative using the second derivative test. The second derivative is 2, right? Taking the derivative of the first derivative, we just get an answer of 2. So if we evaluate g double prime of 3 over 2, the answer is 2 because there's nothing to plug in. So no matter what we did g double prime of, we would always get 2, which is always going to be positive. So this means there is a relative min. A relative min at x equals 3 over 2. So let's kind of think about what this means. We should have actually known that, right? We know that x squared minus 3x plus 1 is a parabola. We know it's a parabola that's opening upward. So if it's a parabola opening up, then the value here would have to be a relative minimum value. But we just showed that it was using the second derivative test. Okay, so sticking with information from the second derivative, that brings us to concavity and inflection points. So take a look at these two graphs, graph A and graph B. Both of these graphs are increasing, right? But they are increasing in different ways. They are increasing at different rates. The graph A is increasing at an increasing rate. The tangent line would be becoming steeper and steeper, where graph B is increasing at a decreasing rate, meaning the tangent line would be becoming more and more flat, closer and closer to being horizontal. So this is the type of information that we can find from the second derivative. So this is saying, for example, going back to this first graph, since the slope is increasing, we're checking the rate of change of the first derivative, which is the second derivative. So another way we can think about it is for the first curve, if we have a tangent line, let's put a tangent line somewhere. So here's the tangent line. The curve is above the tangent line, so that means this one is concave up. For B, if we put a tangent line somewhere, now the curve is below the tangent line, so that means it's concave down. Another way we can think about it too, concave up, the most basic kind of looking concave up would look like that, opening up. Concave down would be like that, opening down. But it can get a little tricky because obviously these two curves don't look exactly like that, but you can see how they're kind of segments of that. Okay, so the definition is exactly what we pretty much just mentioned up here. We say that it's concave up if the curve is above the tangent lines. We say that it's concave down if the curve is below the tangent lines on some interval. So let's see an example here. So we have all of these different intervals. Taking a look at this first interval, A to B, we can see that it's concave down. So also, all right here, concave up, we can abbreviate CU or CCU. Concave down, we're going to abbreviate CD or CCD. Okay, so for that first interval, it's concave down because the curve would be below the tangent line. And then we get to this point right here where it changes concavity. And then for this interval, it's concave up because the curve is above the tangent line. For the next interval, it's concave down because the curve is below the tangent line. The next interval is concave up because the curve is above the tangent line. Next one is concave up for the same reason. Last one is concave down because the curve is below the tangent line. Okay, so concave up, it's opening up. Concave down, it is opening down. So that brings us to the test for concavity. How do we test for concavity? Well, concavity is going to be if f double prime is positive over an interval, that means concave up. If f double prime is negative over the interval, that means the function is concave down. So let's think about what that means. F double prime is positive. That means the slope is increasing. The first derivative is increasing, so it's concave up. If f double prime is negative, that means the slope or the first derivative is decreasing, which means it would be concave down. So let's see an example. The figure below shows a population graph for honeybees. How does the rate of population increase, change over time? When is the rate the highest? Over what intervals is P concave up or concave down? So how does the rate of population increase change over time? So we can see this whole curve is increasing the whole way, right? It's rising left to right, but we can see the rate at which it increases is changing. And that's where the second derivative comes into play. The second derivative comes into play when we are seeing how the rate of change changes. So taking a look at this graph from 0 to, it looks like 12, it looks like the rate of increase is increasing. So the slope is increasing, and then once it hits t equals 12, then the slope starts decreasing. So it doesn't mean that the curve is decreasing, but the rate at which it's increasing is decreasing. It is increasing at an increasing rate until it hits 12, and then it begins increasing at a decreasing rate. Okay, and then the next question on here, when is the increase rate the highest? Well, it looks like it's going to have the highest increase rate at t equals 12 weeks. The easiest way to think about this is that the slope of the tangent line here would be the steepest, right? If you put a tangent line everywhere on this graph that you possibly could, the one at t equals 12 weeks would be the steepest slope. And then the last question was for concavity. What intervals is this concave up, concave down? Well, we can go ahead and see that from 0 to 12, it's concave up, because if we put a tangent line anywhere, it would be, the curve would be above the tangent line, and then from 12 to 18, it would be concave down because the curve is below the tangent line. Also, once again, it looks like it's opening up for here, and then it's opening down on the other side. So concave up on the interval 0 to 12, concave down on the interval 12 to 18, and I wrote that in interval notation. Okay, so now that brings us to inflection point. When a curve, let's go back to what we just did at t equals 12 right here. It changed concavity, right? It went from concave up to concave down. That point is called an inflection point. When a curve changes from concave up or concave down or vice versa, that means there is an inflection point at that point. So the way that we have to find inflection points is right here. We're going to take the second derivative and set it equal to 0 and solve. Also, we're going to see when the second derivative does not exist. At those points, at those x values, there may be an inflection point, but we have to check using a number line just like we did for the first derivative test. So what we're doing is nearly identical to the first derivative test, except we're doing it to the second derivative and it tells us different information. So let's see this example before we do one of our own. Sketch a possible graph of the function that satisfies these conditions. First one, f of 0 is 0, f of 2 is 3, f of 4 is 6. So those are obvious, right? Those are just x, y ordered pairs. Now we also have that f prime of 0 equals 0 and f prime of 4 equals 0. So this means there will be a horizontal tangent line at these points, and it's possible that they're relative max and relative min, but we don't necessarily know for sure just yet. Let's see the other information. So the other information we have, f prime is going to be positive between 0 and 4, and f prime is negative elsewhere. So if f prime is positive, that means the function is increasing. So positive derivative over an interval means the function is increasing over that interval. And if the derivative is negative, that means f of x is decreasing over that interval. Okay, and then the last one for 3, we have f double prime is positive for x greater than 2. If f double prime is positive, that means f of x is concave up over that interval. And if f double prime is negative for x greater than 2, that means f of x is concave down over that interval. So here's the graph. There's not necessarily, obviously, one exact graph for it, but this one will satisfy all those conditions. We have our points plotted, 0, 0, 2, 3, 4, 6. We have it decreasing increasing, decreasing. And then lastly, with the concavity, we have it concave up, and then we have it concave down. Okay, so now let's do an example, 2 examples where we're putting all of this together. So we have the function y equals x to the 4th minus 4x cubed, and we want to find concavity, points of inflection, intervals for increasing, decreasing, and any local max or min. And then we're going to sketch this curve. So I'm going to chop this page up into halves. The left half is going to be using the first derivative. It's going to be the first derivative test. I'm going to find intervals for increasing and decreasing, and then the local max and min. So first we have to find the derivative. So that's going to be y prime is going to be 4x cubed minus 12x squared. And now to find the critical values, we need to set y prime equal to 0 and solve. So we set this equal to 0, 4x cubed minus 12x squared equals 0. And now we go ahead and factor out a 4x squared. We'd be left with x minus 3. Set both of these equal to 0 separately. We get x equals 0 and x equals 3. So these are going to be our critical numbers. And also notice for our critical numbers, we would usually have to see when the derivative does not exist, except the derivative here is a polynomial. So once again, like we saw before, it's going to exist for all real numbers. Okay, so we don't have to worry about that at all. We have our critical numbers. Let's go ahead and set up our interval, or our number line for increasing, decreasing. So I'm going to go ahead and set this up. We have our critical numbers 0, 3. The bottom portion is going to be y prime, and we're going to see how that affects y. Okay, so now we need to pick numbers for our test numbers right here, here, and here for every interval that we have. And let's pick -1, 1, and 4. So we would have to plug in these values into y prime. And I'm going to show you guys a little bit of a nice shortcut. So when let's say we evaluated, we know that y is 4x, or y prime is 4x cubed minus 12x squared. If we're trying to evaluate y prime of -1, instead of plugging it in directly into here, we can actually use the factored version, which was 4x squared times x minus 3. And now we can kind of eyeball it, because if we do 4 times -1 squared times -1 minus 3, what you can say is that this will be positive. -1 squared is positive, times 4 is positive. This will be negative. -1 minus 3 is negative. Positive times a negative is negative. So that's a nice way, if you can use a factored form, then you can kind of do it in your head without actually having to crunch the numbers. So that's negative, so it is decreasing for y over that interval. Okay, and then I recommend trying that same way with these numbers right here, y prime of 1. We would see that this is actually going to be negative as well. And then y prime of 4 will be positive. Okay, so it's going to be positive for that interval, means y is increasing, negative for this interval, which means y is decreasing. Oh, sorry, I just reversed that. Got to reverse those numbers. It was negative for this interval, which means y is decreasing, positive for this one, which means y is increasing. Okay, I'm just going to go ahead and erase my work here so I have room. Okay, so we just condensed it up. Now let's go ahead and see these intervals for increasing, decreasing, and any relative max or relative min. So we're decreasing for this interval right here. That's from -infinity to 0, union 0 to 3. And then we are increasing for this interval right here, which is 3 to infinity. Okay, and then we have a relative min. we have a relative min or a local min at the value of x value of 3. If you go ahead and plug it into the original function to get the y value out, you would get negative 27. So there's no relative max because it doesn't change from increasing to decreasing anywhere. It just changes from decreasing to increasing. So there's our information from the first derivative test. We could have also done the second derivative test here to determine the relative min in this case, but since we were already needed the intervals for increasing and decreasing, you might as well just use the first derivative test here instead. So now let's go ahead and find the intervals for concavity and inflection points. Okay, so let's go ahead and take the second derivative. So taking the second derivative of y, taking it off of the first derivative here, we get 12x squared minus 24x. And now we're going to set the second derivative equal to 0. So we set the second derivative equal to 0, and we can factor out a 12x. We'd be left with x minus 2. Setting both of those equal to 0, we would get x equals 0 and x equals 2. So hopefully we can see how these methods so far are pretty much the same. We take the first derivative, set it equal to 0, take the second derivative separately, set it equal to 0, and we're going to create a number line just like we did before. Create a number line with our values of 0 and 2, and now it's going to be y double prime down here. How does that affect the graph of y? And also what we should mention is that y double prime exists everywhere, because remember that technically these points, these aren't called critical points, but these points that we would put down here on this little number line would have to be when the second derivative does not exist. Since the second derivative is also a polynomial, it exists everywhere, so we don't need to worry about that for this question. Same thing as the first derivative. Okay, so we go ahead and we pick our values to plug in, our test values here, maybe -1, maybe +1, maybe 3. And then we would plug them in the function in y double prime. And I'll leave that to you guys to test. If we did, we would have to evaluate y double prime of -1, y double prime of 1, and y double prime of 3. We would get y double prime of -1 is positive, y double prime of 1 is negative, y double prime of 3 is positive. So that would be positive, negative, positive. So if y double prime is positive, that means y is concave up. So I like to draw it like this, concave up. You can just write CU. Then it means this interval is concave down. And then lastly, this interval is concave up. So let's go ahead and write down our intervals for concavity. I'll put CU for concave up. The intervals for concave up we have here and here. That's going to be -infinity to 0, union 2 to infinity. And then the interval for concave down is going to be right here in the middle, which is from 0 to 2. So now, lastly, taking a look at inflection points, we need, for inflection points, it's going to be when it changes concavity. It changes concavity at 0 and at 2. It changes from concave up to concave down, back to concave up. So since it changes concavity, those are both going to be our inflection points. And I'll leave it to you guys, but it would be find the y values by plugging them back into the function. So 0, 0 and 2, -16. So hopefully this also doesn't look confusing. The inflection points in the relative min, these are x, y ordered pairs For the intervals for increasing, decreasing, and concavity, that's interval notation. So it looks the same, but they represent two different things, two different types of notation. So here's the function that we have right here. We have the inflection points, we have the relative min, we have decreasing and then increasing, we have concavity, concave up, concave down, concave up, so we have everything right in this picture. Okay, so let's do one more example. Let's sketch the graph of f of x equals x to the 2/3 times 6 minus x to the 1/3. So we're going to do the same thing we just did. We're going to split it up and do the first derivative test here on the left for intervals for increasing, decreasing, and relative max and min. And then on the right, we're going to use the second derivative to find intervals for concavity and inflection points. So don't get confused and call this the second derivative test over here on the right. Remember, the second derivative test is used for finding relative max and relative min, but since we're finding intervals for increasing and decreasing, we might as well just use the first derivative test. Okay, let's go ahead and take the derivative. So for the sake of time here, I'm not going to go through and do step by step for the derivative. I recommend you try it out on your own. It would be the product rule, because we have our two factors. So the product rule would be the main rule. Inside the product rule, we would need the chain rule. Inside of both of those, we would need the power rule. So it's kind of messy. Afterwards, you could combine it into one fraction, and if we did that, we would get this right here. F prime is 4 minus x divided by x to the 1/3 times 6 minus x to the 2/3. So next, we're going to set f prime equal to 0 to find the critical numbers. So that's 4 minus x over x to the 1/3 times 6 minus x to the 2/3 equals 0. So one of the reasons why we combined it to look nice like this into one fraction, because if you go through and you do it yourself, you'll see it won't look like that right away, is because when you set it equal to 0 now, it's going to make these next steps a lot easier. So setting this equal to 0, the only way a simplified fraction equals 0 is if the numerator equals 0. So you set the numerator equal to 0, we add x to both sides, and we get x equals 4. So the next thing that we have to actually worry about for this one is finding critical numbers. We have to remember we have to find when the derivative is undefined. This one will be undefined when the denominator equals 0, because we can't divide by 0. So we're going to go ahead and set that denominator equal to 0, and that's going to be x to the 1/3 times 6 minus x to the 2/3 equals 0. This would be zero product property. This is also one that you could do in your head. Set both of these equal to 0 and solve. We would end up getting x equals 0 and x equals 6. So here are our critical numbers. So we can go ahead and make our number line. So we have f prime down here, f on top. We have 0, 4, and 6. We can choose our test values in here. And for these test points, actually, I'll leave it to you guys to pick some test points. We should end up getting, this would be negative, so f would be decreasing. This would be positive, f would be increasing. And then these last two intervals would be negative, so f would be decreasing. Okay, and then from that we can find our intervals for increasing, decreasing, and local max, local min. So it's increasing from 0 to 4. It is decreasing at all other intervals. So that's negative infinity to 0, union 4 to 6, union 6 to infinity. And local max, we do have a local max at 4, x equals 4, because it changes from increasing to decreasing. If you went ahead and you plugged it in the function to get out the y value, it ends up simplifying to a fraction you would end up, or a decimal you'd end up getting. So I just leave it as 2 to the 5/3. We do have a local minimum right here at x equals 0 because it changes from decreasing to increasing. And if you plug that in the function, you get a y value of 0. So that's all of our information from the first derivative. Let's do something similar with the second derivative. And if we are taking the second derivative, we're actually going to need a whole bunch of stuff. We would need quotient rule first, and then product rule and chain rule and power rule within that. So to save us from that, we can just go ahead and write that down. So if we did all that, we would get f double prime is -8 over x to the 4/3 times 6 minus x to the 5/3. And we do set this equal to 0. So the only way that this is going to be equal to 0 is if the numerator equals 0. Once again, simplified fraction. So the numerator equals 0 would be -8 equals 0. -8 obviously does not equal 0. So there's nothing to solve for. So that means f double prime will never equal 0. Now we also need to take into consideration when f double prime is undefined. And just like from the first derivative test, the second derivative will be undefined when the denominator equals 0. So if we set this equal to 0, the denominator for the second derivative, we solve both of those separately. We get 0 and 6. Okay, so we go ahead, we set up our number line using just 0 and 6. And we have f double prime down here, capital F, or the regular function up top. We would pick values in here for our test values, but just for time's sake, we'll skip doing that, and I'll leave that to you guys. We would get negative, negative, positive. So if f double prime is negative, that means f is concave down. So it's concave down over these two intervals, and then f double prime is positive for the last one, which means f is concave up. Okay, so now we have all of our information. Let's see our intervals for concavity, concave up, concave down, and let's see an inflection point. So we know it's concave up from 6 to infinity. We know it's concave down from -infinity to 0, union 0 to 6. And then inflection point, when it changes concavity at 6. And if we want the y value for that, we obviously plug it in the original function. That would give us a y value out of 0. And if we actually take a look at the graph, we have our inflection point right there, 6, 0. That actually ends up being a vertical tangent line directly at that point. And you'll see that everything else is taken care of. We have a relative max right here at x equals 4. We have a relative min at the origin. We are decreasing, increasing, decreasing. And concavity, it is concave down, concave down, concave down again, and then concave up. Okay, so that takes care of that example. And then for the last thing here, just a little quick summary, just because there was kind of a lot there. Summary, we have f prime and f double prime. F prime can help us determine the intervals for increasing and decreasing, as well as the relative max and relative min using the first derivative test. And then we can use f double prime to help us find the relative max and relative min also using the second derivative test. So we would only have to use one of these tests to find the relative max or relative min. From the second derivative, we can also find where the function is concave up or concave down, and then we can also find any inflection points. Okay, so that is it for this chapter.